Hello, we're going to have a repeat performance today because not everyone was able to get the talk last time it was presented. So today's talk is again given by Marius Kadek, and the title is A Bird's Eye View of Solids and Band Structures. So go ahead, please, Marius.
A microphone. Please switch off microphone in Oslo, if you have not done so. Oslo?
It seems quiet enough in Oslo.
Have you switched off microphone?
Yes, this.
It was on.
Yeah, no, that's it on. Yeah.
Okay, well, we'll have it switched off if it bothers us. Go ahead, please, Marius.
So, some physicists, when they approach a problem or a question in solid-state physics, they address the issue by creating a model, simplifying reality and best describing the situation. Now, I found this quote by Fulde in '93. He basically says that methods based on systematic improvements of accuracy are not as common or developed in solid-state physics as they are in quantum chemistry. Now, I think one of the reasons for this might be that there is somewhat more numerics involved, and perhaps it's a bit more challenging to get the same or comparable accuracy. Okay. Of course, there are calculations, ab initio calculations, also done in solid-state physics, but almost all of them, if not all of them, are done with plane waves for one-particle basis functions. Now, plane waves are very well suited to describe solids because of their diffuse nature, but they are notoriously ill at describing regions close to nuclei around cores, which makes studying core spectroscopies or correlated properties and the inclusion of relativistic effects cumbersome. Not impossible, but perhaps cumbersome. Now, relativistic effects are very important also in solid-state physics for the same reason as they are important in chemistry, and that's heavy elements. Heavy elements tend to make relativistic effects stronger. And this is also a situation in solid state, mostly because there is spin-orbital interaction in the relativistic world, and spin operator does not commute with Hamiltonian, which changes the symmetry situation in relativistic world, which can have a very qualitative consequences on the results in solid state. One example of this is graphene, where on the picture in the left, we have the upper cone is a conducting band and the lower cone is a valence band touching each other in one point, which makes graphene a conductor, rather a conductor. Whereas if you include spin-orbital interaction, then there is a band gap between the conducting and valence band. And band gap is very small, but it is there, and this makes graphene an insulator, or rather a semiconductor. And the carbon is not a heavy element, it's actually very light, and the picture changes even much more dramatically for heavier elements. Okay, so the importance of relativistic effects is there. Now, my research project, or main PhD topic, is based on a belief, a hope that there is a gap to be filled. Namely, I am to develop a method using Gaussians centered at atoms, with inclusion of relativistic effects on solids. Now, to this end, I must admit that there is one alternative approach. It is possible to do an all-electron calculation with plane waves, and thus also include the relativistic effects. That's how they did the graphene. And it's a combination of plane waves and spherical harmonics to account for the regions close to nuclei. Now, which approach will be better, more convenient, remains to be seen, whether Gaussian type orbitals or plane waves in combination with the spherical harmonics remains to be seen. That's why I said the hope. So, I'm interested in crystals, or solids are, to some idealization, infinite periodic systems in 1, 2, or 3 dimensions. So these are the superstars of my daily work. So everybody knows what a crystal is. So what is an ideal crystal, which is also quite common? So you take a an atom or a set of atoms and you place them somehow. It can be a molecule. And this is what we call a motif or a unit cell. And you also take a set of points infinite set of points in 1, 2, or 3 dimensions, periodic. And at each, this would be called a lattice. And at each point, you replicate the unit cell up to infinity. And you create a perfect translational invariant system, and that's called ideal crystal. Now, of course, real crystals are not like this. They have surfaces, fractures, some extra atoms in the lattice, some missing atoms. And all these effects would make the crystal real, but they violate the translation symmetry. But they can be studied as perturbation to the ideal crystal. So what's so good about the ideal crystal? There are 2 reasons. First is that we can exploit this perfect symmetry computationally, deep in the algorithm. We can make it go faster if we exploit the symmetry. And second, we can also exploit the symmetry in an interpretational way when giving interpretation to results. This would be called the band structure I will show in the end. Okay, so now what I actually do is electronic ground state optimization, which is a common name, but it's a standard self-consistent field theory in a one Slater determinant framework, which means either Hartree-Fock or Kohn-Sham DFT. And these steps, as they are written there, are almost exactly the same as in the molecular world. Okay, so it's always, you first evaluate integrals, then you can use the integrals to construct the potential, so-called Fock matrix. Then you transform to Casebased. I will explain this later. You diagonalize the Fock matrix and then construct a new density in the real space. And from this point of view, it's exactly the same as on molecules, with the exception of the transformation to Casebased. Okay, the rest of this talk I will dedicate to very briefly sketching some major conceptual differences between studying solids and molecules. And they are indeed in almost all of these steps except the first one. So let's start with the first one, which is integral evaluation. So as I said, we use Gaussian functions. And in order to construct the Hamiltonian or the potential, we need 1 and 2 electron integrals, which are written there. Since chi are Gaussian functions, then these integrals are exactly the same as on molecules. I just translate them. I just do the lattice translations, but they're essentially the very same thing as on a molecule. So this part I don't have to do myself. I'm implementing this into Respect program, where I enjoy a highly optimized integral package, also on the relativistic 4-component framework, which I will use later. So this is the one part I actually don't have to deal with when doing solids, because it's exactly the same as on molecules. And which is very good, because the rest of it I have to write basically from scratch. And I must say that this is only the case if the code is truly modular. So if the integral part is truly separate from the rest, from the construction of the potential. Otherwise, it might be complicated to do this. Okay? So now what I actually do is the construction of the potential, which is the second step, once I have the integrals. So this is the most complicated part, and I'm spending most time on this. The equation there is written for Hartree-Fock operator, and it is implicit summation over doubly occurring indices is assumed. Now I will explain some differences that are there. So first of all, it's translation symmetry, as I mentioned before. This means that indices A and B are not handled on equal grounds. I always fix the index A for the reference cell, and then I translate only the index B, which makes the algorithm a bit different. In a molecular world, they can be handled as both same Gaussian type orbitals without any translations. Okay. Second difference would be lattice summation. Since we now have a contractions with the density, and since the system is infinite, then we have something called infinite summation or lattice summation, which is actually the most tricky part. This only happens in the 2-electron part of the Fock operator, which means Coulomb and exchange. And also in the Kohn-Sham theory, it will also be exchange correlation. So these 3 are most complicated, of which exchange correlation should be the simplest. But I haven't done that yet, so I can't really say. And Coulomb and exact exchange on the Hartree-Fock level are the most complicated. Now, apart from theoretical differences, there are two nasty features of practical nature when dealing with this kind of work. First nasty feature is that it's already a numerical procedure, already at this level when constructing the Fock operator. So in a molecular world, where there are no infinite summations, you can write an algorithm, very simple one, that contracts the integrals with the density, and you can get a reference exact Fock matrix. So you can have some reference result and you can later compare with when doing better algorithms or faster. This is a luxury I don't enjoy in solid state, because no matter what I do, I have to truncate the infinite summations in some way. And the whole procedure is very sensitive to the way I truncate them. So already at the Fock matrix, or the potential, is approximate. And as I said, it can be very sensitive to the way the summations are handled. So on Coulomb, for example, is divergent, but it can be easily made convergent, but still it's only very slowly convergent. And actually the summation can be written in various ways, and depending on how it's truncated, the result converges to a different energy if there is a dipole moment in the unit cell. I will talk about this later in more detail. The second term, exchange, is convergent, but is the only term in the entire framework, convergence of which relies heavily on the properties of density matrix. So sometimes it happens that if the density matrix does not have a very good decays, then exchange can resemble some very catastrophic behavior. Okay, so as I said, it's very tricky getting the summation. This is probably the major difference between the molecular world and on solids. A second nasty feature is a computational complexity. There is a table where I showed the total number of integrals needed. Now, capital N is the total number of unit cells, and the lowercase n is the number of basis functions per unit cell. Of course, electron-electron integrals are most dominant when it comes to this. And here I must say that despite the fact that most of these contributions give absolutely negligible contributions to Fock matrix, then unless the scaling of the method is truly better than the one in the table, then it might be very, very difficult to do 2 or 3 dimensional systems. So 1 dimensional should be fine, but 2 or 3 dimensionals can be very time consuming if the scaling is truly not reduced. So there's no such thing as a small system in solids, because they have to be infinite and the n has to be sufficiently large. Okay, second step, or the third, if I have the potential now, it's going to be a bit perhaps easier, is the transformation to Casebased and then the SCF step. So since the system is translation symmetric, we can use this symmetry, and this symmetry has a consequence on the wave functions or on your orbitals. The consequence is called Bloch's theorem, and it's the equation written there. M is the lattice index. Okay, so if you translate your orbital, you get this phase factor times the same function, because now Hamiltonian and translation operators have the same eigenfunctions. And we can use this to construct a symmetry-adapted basis, which would be called a basis in the Casebased of Bloch-like functions. So chi are our Gaussian functions, and now phi is a symmetry-adapted function. Then we express every operator and element in the SCF equation with respect to this basis, and this is called a Casebased representation. And then we solve the SCF equation. This has a great advantage, this Casebased, because everything becomes block diagonal, mostly the Fock matrix. So we only block, we already have a block diagonal Fock matrix. We only do several diagonalizations. Now there's one extra and final issue here, that even if you can do all infinite summations in the real space very, very accurately or exactly, and even if you can get an excellent representation of the Fock matrix of the potential, then because the system is infinite, and so is the number of K points is also infinite. So you would have to do infinitely many diagonalizations for infinitely many blocks of Fock matrix. So for this reason, a slightly different condition is chosen, stronger than the Bloch theorem. It is called periodic boundary condition, which is often emphasized in connection with solid state. In my opinion, it's a bit perhaps misleading, because since the system is infinite, it has no boundaries. So why are there periodic boundary conditions? So they actually make the system finite in a way. I will demonstrate in one example what this means, this periodic boundary condition. So this is a two-dimensional plane, which should be infinite, and it contains unit cells in a two-dimensional way, okay, as an example. Now, if we make it finite, so we just take this piece of a plane, and then we assume an extra condition on the wave function, then on the upper side, it equals on the lower side, and on the left is the same as on the right, the wave function. It's an extra periodicity that is not there before, but now we postulate it. And if we actually do it with the plane, connect the upper part with the lower part, then we get a cylinder. And if we connect the left with the right on the cylinder, we get something called torus. So this changes the topology of the system dramatically. Now, I believe that because of the lot of numerical steps involved in the procedure, this is not essentially the same thing as infinite system. And this can introduce some artifacts that can be observed during. This is the case for Hartree-Fock and Consham, the SCF step, how it is actually handled numerically. But this is only the case if the number of unit cells is not large enough. If the supercell of all your unit cells is not large enough, then you may see some artifacts. So this, of course, needs to be handled by taking large enough supercell. Okay, and finally, as an example, I will show one result. It's an infinite system called polyacetylene, 4 atoms in a unit cell, periodically repeated along one dimension. So it's a one-dimensional system. And we have a single and double bonds between carbon atoms, alternating in length. So we have a difference in the bond length. Okay. And these are results I got on the Hartree-Fock level. So this we call the band structure, and it essentially means that now we have our index K, which enumerates our irreducible representations. And since it's a one-dimensional system, we can put this one-dimensional K on the x-axis and orbital or band energies on the y-axis, and we get this diagram, which is called the band structure. Now, the blueberries on those bands are doubly occupied states with electrons, and now we see that we only have fully occupied bands and fully vacant bands, which means that this system would be an insulator, because there is a finite band gap between a conducting and valence band. So this is one of the results that we can get. Actually, if you run a calculation without bond length alternation or with 0 bond length alternation, so equal length between all carbon atoms, then the band gap vanishes and the system becomes metallic. So that's quite an interesting feature. So these band structures are perhaps the most interesting results from this ground state optimization. If you're not aiming for properties, which might be the case later, for example, then apart from the total energy or cohesive energy, this band structure is perhaps the most interesting thing. On the picture on the right is density of states, and maybe I will talk about that some other day. Okay, that's another thing. Okay, finally, I would like to thank Michal and Stano as main authors of RESPECT program, and Kenneth Root as my supervisor, and you for your attention.
Thank you, Marius, for the talk. We'll
switch on.
We will open the floor for questions. Are there any questions from Tromsø? How about in Oslo? Do you have any questions there?
I have a question.
There is one question. Go ahead, please.
So it's quite general. So when you say you make 2-dimensional and 3-dimensional, then you have more number of integrals to compute, or can you replicate, just put the same integral as you get in 1 dimension in 3 places?
I'm not sure I understood the question. If I can do 2 or 3 dimensions?
So what I don't get now, so you have a cubical box in one dimension, like many unit cells.
Yeah.
And that you call one-dimensional system. And what happens when you say that dimension is three-dimensional? It's just that everywhere in a space you have a cube unit cell.
Yeah. So I replicate the box only along the one dimension. The system is infinite only in one dimension. It can be a three-dimensional molecule, but it's replicated only in one dimension. That's what I would call one.
Yeah, so unit cell is replicated in one direction. So if you have three-dimensional, can you just put the integral of the one-dimensional in another two? So you don't need to compute it, you just put the same one, because if you see each dimension, it could be only one dimension and then you just add it, sum it up sort of thing.
Yeah, you can.
No, I don't think this can be done in that simple way, if I understand correctly. So for higher dimensions, I have to replicate the unit cell in either both two or all three dimensions, and then I have to run the calculation again.
No, but what I meant is, like, since you have a periodic system, you have a unit cell placed equally. So in one dimension, the integral will be like dependent on distance, parameter will be distance placed in the unit cell. And if you do it in three dimensions, then you have the same distance with the another. Yeah, it could be some integral could be different, but it might be that you get the same function.
It kind of depends if your unit cell is square or not.
So I mean cubic.
In a cubic unit cell, then as the repetition in either direction is the same. Translation, then you will be able to reuse some integrals.
Yeah, that's what I meant.
Yeah.
That if you are a cubic one, so the distance would remain same in all the directions.
So instead of
some of this symmetry of a cubic lattice. Cubic is a very special type of lattice. This can be exploited. That some integrals would indeed be the same, but still there would be quite a lot of integrals that would be different.
Okay. No,
but yes, this symmetry can be exploited extra. Yeah.
Okay.
I was wondering for this system that you showed, the
Polyacetal.
You said that in the form where it is now, it is not conducting.
Yeah.
All right. But then you said if you have no bond length alternation, then it would be conductive.
Yeah.
All right.
So the band gap slowly starts vanishing.
Okay. Maybe I'm mixing up a few things here.
So a conducting system would require a partially filled bond. So, for example, if the Fermi energy was up here and the blueberries were plotted here, and there would be empty here, then it would be a conductor because infinitesimal voltage would make the electrons flow.
Okay.
This is the one electron picture.
I'm mixing up two things here. I realized for the vibrational motions, those systems are very good at working as antennas to kind of push. The modes that you see with those kinds of systems typically involve the entire molecule, so I thought there might be some connection between that and conduction. But probably not. So.
Yeah. Okay.
All right. Well, anyway, are there any more questions?
Yeah, this same slide. Have you compared the energy with some medium oligomers, for example? For example, in many papers, these polymer type molecules are considered, or they are calculating for oligomers up to 8 single molecules or octamers. How does it compare? For example, instead of this cohesive energy, I would like to know how this total energy changes compared to octamers, for example.
Okay, I haven't tried that, but I think that the cohesive energy becomes similar order of magnitude, but the number would be different. I would expect the number to be different, but not by orders of magnitude, perhaps.
But it will be nicer if we check it, because there are many papers on this kind of studies.
Well, thanks. I'll try.
Okay, then I'll ask once again, are there any more questions in Tromsø? How about in Oslo? That does not seem to be the case, and that means that we are done for today, so let's thank the speaker again. And I would like to wish everyone a nice weekend.
Yep.
Goodbye.
Goodbye.